In this lecture, we are going to talk about the compressibility of soils. So, compressibility means volume changes in response to stress changes. So, this can be due to one-dimensional stress change or all-round stress change. And the difference is going to be just in the soil parameters. So, if it is a one-dimensional case, then your volumetric strain, which is change in volume over initial volume, is simply going to be equal to change in height over initial height. And basically that's it. Other than that, there is nothing special to it. And if we also consider it in terms of void ratios, it will be this. So the initial methods or models consider the soil to behave in a linear manner, linearly elastic manner even. So and of course I need to mention it happens due to effective stress changes because we are compressing the solid structure. So the initial, the most primitive approach to this is a coefficient, a constant, times change in effective stress. So here we need to note this is called the coefficient of volume compressibility. And if you work out the units, this is stress, so this is inverse of stress. And if you look at the definition, it looks like it might be inverse of something like a modulus, but it is not going to be inverse of modulus of elasticity though. It is going to be something else, not so note that it is in terms of meter square per kilonewton, for example, and it is definitely not equal to 1 over Young's modulus. And this is also not equal to 1 over bulk modulus either, because here strain is defined in volumetric terms, but stress increase is defined in a one-dimensional, as a one-dimensional term. So basically here what we are talking about is you have an element of soil that you apply a stress increase. Of course, for it to be balanced, it has to be on the other side as well. So, and when you say one-dimensional case, it means the other dimension, in the other dimensions, the soil isn't moving. So to the sides, it is fixed. It cannot move to the sides, and it is simply moving in the vertical direction. So that's why it is different than both of these, because in modulus of elasticity, it would be free to move to the sides. In bulk modulus, your stress increase would have to be in all directions. I'm hoping or assuming you know these from past courses like strength of materials or material science courses. So here this, yeah, it can be related to the other parameters through including Poisson's ratio and so on, but it is definitely not the same thing. And the other thing I would like to note is this would be change in effective stress. So let's say change in vertical effective stress and this would be equal to change in total stress in drained condition. So if you are looking at a fine soil, when you apply the stress, this is not going to happen because the total stress increase you apply will be taken by the pore pressures, not effective stresses. So remember that if you want to talk about a fine soil, this would be the volume change that will happen a long time later once it moves into the drained mode. So yeah, that's one model and it is useful, but it is useful for the small stress changes relative to the initial stress you have in your soil. The reason for that is because soils behave non-linearly. So what does that mean? That means you cannot express it with a linear relationship like this. So as decades passed, people noticed the for example, if you plot stress, effective stress versus strain, people notice soils generally harden as you increase the stress. You cannot fail the soil really because it is confined on two sides, so you will always be compressing the grains together, and as you compress the grains together, more grains will touch each other. More grains will press against each other with greater normal stresses, so they will be less able to move around each other, and their contact areas will also grow as well as you increase stress. So you will also be increasing strength of those contacts both in normal and shear directions. So what that means is, as you increase the stress, you have to increase the stress a lot more to get some strain. But yeah, this is basically, if you are just looking at a small increase of stress, then you can, between those points, you can model it like a line, and then you won't be making too much error. And actually, this is why MV, as you see from here, MV is a function of stress as well. So you can also see this, for example, in soil investigation reports or laboratory results, where they just write, they just give MV in the form of a table. For example, 0 to 50 kPa, MV is something, 50 to 100, MV is something else, 100 to 200, MV is something else, and so on. And you will see that these numbers are going to be decreasing in order. So obviously there needs to be a better model than this. And if you have a curved plot like this, you can always try to see what happens if you uncurve it by taking logarithm. And in order to make things more characteristic, because when you say strain, it starts from some volume, and its behavior will change according to where you start from. So instead of that, it is better, in order to characterize it, it's better to plot things in terms of void ratio. So if you plot in terms of void ratio versus logarithm of stress, now this brings an interesting plot, because then you end up seeing this behavior. Or rather, this is another soil model. Basically, you can develop soil models, and many soils might obey that. Some soils might not. Soils in the nature have no obligation to obey to your models, because soils haven't taken this course. But basically, this is a good approximation that fits the behavior of many soils. So here, because it is logarithmic scale, it cannot go to, it cannot start from 0, because you don't have 0 in a logarithmic scale, and void ratio cannot be 0, because it's not, if there's no voids, it's not going to be, it's not going to be a soil, it's going to be rock. And commonly we plot these things, we plot this kind of compression plots in an upside down manner like this. I don't know why it is a general convention. It's probably because whenever your soil compresses, it will cause settlement. So your soil surface will be going down. As you compress, your soil surface will go down. So that is probably why you have plots like this. Anyway, so the slope of this is called CC, which is compression index. And if you notice, compression index is going to be unitless. Why is that? Because you have a log scale here. If you have a log scale, the distance you have on the horizontal side is, so this is dE over d log sigma. So void ratio is already unitless. And if you are looking at differences in logarithm of stress, difference in logarithm is log of stress over stress. So from there, you end up with unitless numbers because it's just going to be a ratio of stresses. So for that reason, this compression index is unitless. Now, yeah, okay, this is nice. And again, you have a single parameter to model the compressive behavior, but actually it is not enough because then people noticed that is not all that the soil does. The soil also does this. If you start from a point and unload it, it does this. So as you load, it goes like this, but as you unload, it goes like this. Now, this line I'm going to call virgin compression line. And I can shorten that by VCL. And then from any stress, if I unload it, the grains that have rolled over each other will not roll back up. That's why you don't recover most of that void ratio change, because as you press on the soil, grains will rub against each other and slide over each other, roll over each other, and are going to be displaced. After that happens, there is no recovering that. Well, some of it will be recovered because some of the deformation will be due to elastic deformation of your grain structure. So that is recovered. But most of it is going to be plastic deformation. So slope there is then, so it's going to be again the same definition, d over d log sigma, but it is shown with a different parameter called CS, and that is swelling index. And then if you reload it from here, the soil will do this. And okay, I drew a curve, but I'm putting a slope onto it. The reason for that is because it is usually modeled as a line. And then, very interestingly, if you load it enough, it will continue here. So this CR is decompression or reload index. And they're all the same thing, slope. So they're all d over d log sigma prime. But they happen under different circumstances. And one important bit is that once you reach the virgin compression line in reloading, you once again continue along that. So now that means we might have an additional parameter there, because if you consider a soil in the field, it might or might not be under the maximum stress it has ever experienced. So imagine you have a clay, but 1,000 years ago there was more load on it, or it doesn't have to be 1,000 years, or it can be tens of thousands of years. You can have glaciers on them, but it can also be that I used to have some soil and then I did an excavation 10 years ago, and that's it. Or I used to have a lower water table, so due to capillarity, I used to have a greater effective stress there. Now you have a higher water table, so your stress is less. So by various mechanisms, you can have if your so let's define that actually. Normally consolidated soil. The current stress it has is the largest this soil has ever experienced. Now, as opposed to if you have an over-consolidated soil, and by the way, in books or literature, you often see this consolidation on the consolidated, over-consolidated, associated with fine soils, but it's also true for coarse soils as well. All particulate materials can do this. So the over-consolidated soil means the current stress is less than the largest this soil has experienced in the past. And we also define a maximum past pressure or pre-consolidation pressure as sigma p pre-consolidation or maximum past pressure or stress. And it is that largest this soil has experienced in the past. And it can be now. If it is the normal consolidated version, it is now. So if it is NC soil, your current sigma, and all these stresses are defined in vertical terms. So your current vertical stress is sigma p. If it is OC, then current vertical stress is less than sigma p. So not NC is normally consolidated, OC is over consolidated. Now if you consider okay, first of all, from this point onwards, I'm going to idealize this behavior, this curvy bits, by drawing it like this instead. So it can have a line here. Then if I unload, it goes like this. And if I reload, it will come back on the same line. And then it will continue from here. So I'm going to ignore that curvy bit because it is much easier to do calculations with just lines, and it is not going to be a significant source of error anyway. So not everything else is going to be the same. So here is my CC, and I'm going to say my CR and CS. CR is going to be approximately CS. And of course, they are much smaller than CC. So if you have an OC soil, so this is the same for all soils. The only difference is if you have NC of the same soil, you are already here. If you have an, or anywhere on the line, if you have an OC soil, you are here, or anywhere on the left of the line. So if you consider the behavior of only an over-consolidated soil, so it will do this as you load it. So this introduces one more parameter to our picture. And that parameter is where you are according to or relative to the virgin compression line. So this is your virgin compression line, and here is your sigma p. So your over-consolidated soil is going to deform in a much stiffer way up to the sigma p, up to the pre-consolidation pressure, and then it will continue over the virgin compression line. So you can almost think of this like a yield point. So before that point it is, and if you look at the behavior as well, the way we idealize it, it is going to be like elastic behavior, and then here you are yielding the soil. From this point onward it is going to be plastic behavior. So you can also consider that. But not linearly elastic. Remember, we are still in log space, so it's not linear. Or from as elastic materials. So okay, what if I want to, according to this, what if I want to express the deformations, the strains in terms of all of these parameters then? Let's see. So, okay, in order to help me think about this, let us again draw a generic graph here. So log stress versus void ratio. And if you are doing a normally consolidated soil, then basically this will be it. From here, from this point, I move to this point with a slope of cc. So how much is my strain then? So for NC soil, as I said, sigma 0 is, so I'm going to use sigma 0 and sigma final in this part. So for an NC soil, my sigma 0 is going to be equal to sigma p by definition. And my strains here is going to be, now let's first write, remember this slope is change in void ratio per change in log stress. And I wrote strain, volumetric strain is change in void ratio divided by 1 plus E0. So I can start this by saying Cc over 1 plus E0 times change in the horizontal direction. Change in the horizontal direction is log sigma final minus log sigma 0. But that is simply logarithm of sigma final over sigma 0. And if you are going to convert this to settlements, then you can easily do that. For example, for a layer of given height, you can multiply the strain by height to determine how much that height changes. So anyway, we can generalize it much better if we work it in terms of strains. So this is the normally consolidated version. What about if your soil is over-consolidated? Then you have two possibilities. Then you are somewhere up here, let's say. You can either go from there to here. So for OC, 0 prime is less than sigma p prime. So for case 1, if your sigma final is also less than or equal to sigma p, then what happens? Then it is this blue line. So actually let's denote that like this. Let's denote this by that. Then your sigma 0 is here, and your sigma final is here. So let me put them like this. Yeah, that works. So it goes from here to here. And I can write the same thing, but remember this time I'm using a different slope. Other than that, it is the same equation because it is again the equation of a line. So my sigma vertical, strain vertical is, or volumetric strain is going to be CR divided by 1 plus E0 logarithm sigma final over sigma 0 effective. Now there is another option. If you start from this strain, this initial stress, and go to a higher stress, then what you do is go like this, let's say up to here. So if sigma final is greater than sigma prime, sigma p, then you follow this green line, green broken line. So you first go from sigma 0, you go to sigma p with a slope of CR. So I first go here. Then from there, I move to the next point at a slope of CC. So then from here, I move to there. So where am I moving? I'm moving from sigma p to sigma final now. By the way, these look like huge formulas, but they aren't. As you notice, I'm deriving them just by talking. I'm not even looking at any notes or anything. This is just the equation of a line. And if you are unloading, and actually there's one more way this can happen, and that is if either normally consolidated or over consolidated, doesn't matter. If you are unloading, then so all of these were loading. If sigma final is less than sigma 0, then you are unloading. So in that case, your volumetric strain this time is going to be in the expansion direction. So by the way, these are in soil mechanics, we use positive for compression. So so actually the more correct way of representing these will be have a minus here and also have a minus here. So if the change of void ratio is negative, then your strains are positive. But that usually confuses people. So I'm just putting that minus to make it mathematically correct, but you should just use common sense to decide whether it is minus or plus. If your void ratio is becoming smaller, your soil should be also compressing. And in our sign convention, compression is positive. So just keep that in mind. So here, the volumetric strain this time is going to be CS over 1 plus E0. Remember, in case you decide to model them separately. So usually CS and CR is going to be the same, but if you model with different slopes, then unloading is CS times, again, logarithm of sigma final over sigma 0 prime prime this time, and I'm going to just put a note is positive in compression. So what does this mean then? In practical terms, this means the following. If you have a soil layer, if you are going to model a 1D loading, which means a very wide area load, if it's laid over a wide area, then what's happening here is same as what's happening on the next place. So then it is one-dimensional problem. And if that is the case, you can apply what we have learned here. But the problem is, now as you go deeper, so stress changes with depth. But we found that if you use MV changes with stress. Or if you use the logarithmic bits, then how you deform your soil also changes with depth as well. The compressibility changes with depth. So either way, you don't have a constant strain over depth. The strain will be larger here and smaller here. So the way we address this is we divide it into sublayers. If you are doing this by hand, you can divide it into like 2 or 3 sublayers, usually like maybe 5 meter layers or something like that. But if you, in our age, you have spreadsheets, so you can actually divide it into like 1 meter pieces or even 10 centimeter pieces if you like, because they will all use the same equation. The difference is going to be the stress levels. And then once you divide them into sublayers, then calculate with average values of each sublayer. So stress at mid depth of each layer. So that means you calculate here, you calculate here, you calculate here. And then calculate for each layer. Let's call them H1, sorry, H3. Let's start from the top. H1, H2, H3. Calculate for each layer. HI is going to be, sorry, delta HI is going to be strain I times HI. So strain of, so here you calculate strain 1, strain 2, strain 3 based on stresses at layer 1, stresses at layer 2, stresses at layer 3. And it can be either way. So you can either be calculating with the logarithmic model, or you can be calculating with different MV values, because remember we might have different MV values for different stress levels. So this also works. So you calculate for each layer, you calculate a settlement, and total settlement then becomes sum of those settlements. This is strain, this is summation. So here I'm going to add one more detail actually. If you notice, it's always index over 1 plus E0, index over 1 plus E0. So sometimes some soils, instead of doing this, instead of fitting exactly to this, they fit to a slightly different logarithmic model. And that is, instead of having in terms of void ratio, you can have things in terms of strain. So if you have the same model but with an axis of strain here, then what you get is instead these. So if you plot log stress versus strain instead, then what you can end up with is, for the virgin compression line, what's called compression ratio, and it is simply Cc over 1 plus E0. And then if you are unloading, you have swell ratio, which is simply CS over 1 plus E0. And if you have reloading, then it is RR, and it's called compression ratio, which is CR over 1 plus E0. So if it is with void ratio, the names are index. If it is strain plot, the names are ratio. So the same equations apply, but instead of same equations apply, but instead of each of these, you get to write CR. Here is your RR, and here is your SR. So you can just replace those and they will directly be strain, because this is already the equation for strain. Now I'm going to conclude this with one last reminder. Keep in mind that even if your soil is normally consolidated, if you take a sample out, let's write it here, a sample of NC soil will behave like OC in the lab. Why? Because it was normally consolidated in the site, maybe like 10 meters below the ground. It had 100 kPa effective stress. You took it out, you brought it to the lab. Now it doesn't have 100 kPa stress anymore. So it's going to behave like OC. So if you load it in the lab, you are going to get this and this. But then what you need to consider is this sigma P, is this equal or greater than the sigma prime you calculate in the field. So you need to consider that. Otherwise, every compression test you do in a lab is going to appear like this in the bilinear form, because you always have removed the stress from the soil.